Have you ever stopped to think about how we're literally swimming in a vast ocean of gases every second? I mean, we breathe it in. Balloons float because of it. Even our tires are pumped full of it, but most of the time, we don't even notice.
It's wild when you put it like that. We treat air almost like it's not even there, but so much of our daily life, weather, engineering, even making a cup of coffee depends on the behavior of these invisible gases. I feel like peeling back the curtain on this invisible world could change how we look at almost everything.
Exactly. And today, I want to get into the nuts and bolts. What makes a gas so different from solids and liquids? We've got some handy notes that break down the basics, so let's figure out what's really going on with the air all around us.
I'm all in. And honestly, understanding this isn't just some academic flex. It's the foundation for things like designing ACs or predicting storms. So let's go from states of matter right to the rules that control gases.
So let's start simple. Solids, liquids, and gases. There's this table in our notes that lays it all out, and it actually helps clear up a lot. Like, you take this desk solid, keeps its own shape and volume. Water? That'll take the shape of whatever bottle you pour it into, but its volume stays the same. And then, gas completely free. No fixed shape or volume at all.
What always gets me is how the same substance, say, water, can act so differently as ice, liquid, or steam. Why should something be rock hard one moment and then totally invisible another?
It all comes down to how close the molecules are and how strongly they're holding on to each other. In solids, they're packed tight. In gases, they're barely interested in each other. Those are called intermolecular forces and distances.
That makes a lot of sense. In solids, it's like people jammed into a subway car, barely able to move. But in a gas, it's like people running wild across a field, tons of personal space and total freedom. That helps explain why gases fill any space you give them.
Building on that analogy, imagine compressing a gas. It's so easy compared to squeezing water. That's because those people in the field can get pushed closer with barely any resistance, while in a liquid, everyone's already elbow to elbow.
And that explains density too. Solids and liquids have much higher density because the molecules are packed together, but in gases, most of the space is just empty. That's why we measure gas density in grams per liter instead of per milliliter.
Exactly. And that emptiness is actually why gases are so unique. They're all about freedom of movement. Translational motion, as they call it, lets gas particles zip all over the place, filling up any available space.
You know, that also ties into liquefaction, how you can cool and compress a gas, turning it into a liquid. Even though the attraction between gas molecules is weak, give them a little nudge closer and cooler, and suddenly they stick together. That's kind of amazing.
What blew my mind from the notes is how a gas's volume is mostly just empty space between particles. Unlike solids or liquids, the actual particles in a gas are practically tiny needles compared to the space they occupy.
That emptiness is why Avogadro's law works. No matter if it's light hydrogen or heavy CO2, a liter of any ideal gas at the same pressure and temperature has the same number of molecules because their own size barely matters compared to the volume.
Right, and that concept links up with diffusion and effusion. Diffusion is like spraying perfume. Those gas molecules naturally spread out to fill the whole room. Effusion is more like the slow leak from a balloon, with molecules slipping one at a time through tiny holes.
And don't forget compressibility. With all that empty space, it's easy to pack more gas into a cylinder. Think LPG tanks or scuba tanks. Release the pressure, and the gas spreads out again. It's practical science at work.
You know, another thing that's pretty counterintuitive is how we basically ignore gravity for gases in most lab situations. But gravity is literally what keeps the whole atmosphere wrapped around Earth.
I used to wonder about that too. Turns out in typical lab containers, the molecules are zipping around so fast that gravity barely affects them. Unless you've got a column of gas kilometers high, the density difference from top to bottom is almost nothing.
All right, so we talk a lot about how gases behave, but if we want to measure and predict them, we need numbers. For any gas, we look at four things: mass, often in moles, volume, temperature, and pressure.
Pressure's the tricky one. It's not just a weight pressing down, it's billions of molecules bouncing off container walls every second, like a tiny, non-stop tennis ball bombardment. That's what gives us the measurable force we call pressure.
And to actually measure that, we use barometers, classic mercury columns. The pressure pushes the mercury up, and we read off units like millimeters of mercury or torr. It's old school, but it works. So once we have those variables, pressure, volume, temperature, moles, scientists started figuring out how they relate. The first big breakthrough was Boyle's law, showing that at constant temperature and gas amount, pressure and volume are inversely related.
It's so simple but so powerful. If you double the pressure on a gas and keep temperature steady, the volume shrinks to half. Like squeezing a balloon, the more you push, the smaller it gets.
The math is neat too. We write it as P1V1 equals P2V2. But you do need to watch your units. If pressure is in torr for one measurement and in atmospheres for another, you have to convert them to match.
Great catch. For example, if you start with a gas at 570 torr in 400 milliliters and compress it to 1.5 atmospheres, you need to convert 1.5 atmospheres to 1,140 torr, since 1 atmosphere equals 760 torr. Then you can solve for the new volume.
And sure enough, when you double the pressure, the volume cuts in half just like Boyle predicted. It's elegant, and honestly, kind of satisfying how these rules emerge from the chaos of molecules. So, to wrap this up, all these laws and quirky properties we've discussed are rooted in the idea of an ideal gas, where molecules are just points with no attraction between them. But real gases aren't quite that perfect, are they?
Not by a long shot. When you crank up the pressure and those molecules get close, or when you cool things down and their movement slows, the real attractions and sizes start to matter. That's when the neat rules start to break down.
And honestly, that's the next big frontier, figuring out how and why real gases stray from the ideal. But even with their quirks, these basic rules let us predict so much about the world, from filling scuba tanks to forecasting the weather.
It's a perfect reminder that science is both a tool and a journey. Models help us make sense of the chaos, but there's always more to uncover beneath the surface.